So good morning everyone. Today we are going to extend our discussion related to canonical cover and we'll be having few examples to understand how to compute canonical cover of the set of functional dependencies. And further, we are going to discuss the third normal form. So let's begin with the canonical cover. So let's summarize the facts related to canonical cover. Those we have seen already. So a canonical cover for set F is set of dependencies Fc such that F logically implies all dependencies in Fc and Fc logically implies all dependencies in F. And no functional dependency in Fc contains an extraneous attribute and each left side of functional dependency in Fc is unique. Also, closures of F and Fc are same. So these are important facts related to the canonical cover. So let's formally go through the algorithm to compute canonical cover. So in the last class, we have seen how to find the extraneous attribute in either left hand side or right hand side of functional dependency. And if there exists any extraneous attribute, we need to omit that extraneous attribute from the functional dependency and then we need to add the new dependency in our set. So we have gone through all those details and the procedure. So now how to compute canonical cover systematically. So we are having here the algorithm to compute a canonical cover for set of functional dependencies F. So we are having the iterative algorithm. So what we are going to do first, given F, use the union rule to replace any dependencies in F such that if I am having two dependencies in set F like alpha 1 determining beta 1 and alpha 1 determining beta 2. So in these dependencies, left hand side of the dependency is same. So the first step is apply union rule. If there are such kinds of dependencies in my set F. So apply union rule and come up with the dependency alpha 1 determining beta 1 beta 2. That is the first step to do. What next? Find a functional dependency of the form alpha to beta with an extraneous attribute either in alpha or in beta. If an extraneous attribute is found, then delete it from the dependency alpha determining beta and repeat this process until F does not change further. So till there are changes in the set of functional dependencies F, we need to iterate through. We this that is stable, there are no changes in set F, then we will terminate our algorithm. Note here that union rule may become applicable after some extraneous attributes have been deleted. So it has to be reapplied. So sometimes it may happen that if we are eliminating extraneous attributes from the functional dependency, it happens that for two functional dependencies, my left hand side becomes same. So once again, we need to reapply this union rule for these dependencies. So our algorithm for computing canonical cover is really very simple. First thing is application of union rule, so that if more than one functional dependencies are having the left hand side same, then we can have the union of right hand side of the dependencies, right? And the second step is we need to find out the functional dependency in which either left hand side or the right hand side of the dependency has the extraneous attribute. And if it is possible for us to find out such dependencies, then remove the extraneous attributes in those dependencies and iterate through this process. We get a set. So this is the formal algorithm to compute the canonical cover. If you have any doubts, please let me know. Is that clear? Yes?
Yes, ma'am.
Yes, ma'am.
Fine. So let me proceed now with the example of canonical. So let's find the canonical for the set of functional dependencies F. So we are having the relation schema R with three attributes A, B and C. And the set of functional dependencies F is being provided. So we are having four dependencies in this set F. What we want is, we want to find the canonical cover for this set, right? So we have gone through the algorithm. So what is the first step of algorithm? Yes. What is the first step? Just now we have gone through the algorithm. To apply first the union rule. If there are more than one dependencies having the left hand side similar, that is the first step of our algorithm. So here, given this set F is our first step, we need to check whether more than one dependencies in this set is having the left hand side which is same. So whether we are having more than one dependencies having the left hand side same? Yes. Whether in this set we are having two dependencies for which the left hand side is same.
Yes.
So which are those?
A determines BC and A determines B.
Yes, correct. So we are having two dependencies, A determining BC, A determining B, for which the left hand side of the dependencies is same. So according to the first step, what we need to do is, we need to combine these two dependencies. So we are applying union rule here. And we are coming up with A determining BC. Right? Which is already there in my set. A determining BC. So, ultimately, after combining these two, we'll be having only one dependency for BC. Right? Rest of the functional dependencies will be as it is. So, we'll be having AB to C. We'll be having B to C. And these two are combined as A. Am I clear? Yes?
Yes, ma'am.
Fine. So we have applied this first step now. And we are having now this new modified set. Now, what next we would like to do? What is the next step?
Find
find
functional
out the functional
dependencies.
dependencies such that there is extraneous attribute either in the left hand side or in the right hand side of the functional dependency. So if we look at this set of functional dependencies that we are having two dependencies here for which my left hand side having more than one attribute. For this dependency, my right hand side is having more than one attributes. So what we need to do is, we need to find out if any of these attributes is extraneous. Right?
Yes, ma'am.
Fine. So, we know how to find out the extraneous attribute. Right? In fact, in the last class, we have seen two methods which we can apply to find out whether the attribute is extraneous. So what are these two methods? One method is this. What we can do is, if we want to test whether the attribute is extraneous in left hand side, we can compute alpha minus a closure of that using the dependencies in set F, and then we may check whether this closure alpha minus a plus contains the right hand side of the dependency. If it contains the right hand side of the dependency, then we may declare that A is extraneous. To check the extraneous attribute in right hand side, we are having these steps. What are those steps? We need to compute alpha plus using the dependencies in set F dash. And then we need to check whether my alpha plus contains the attribute under consideration. If yes, then we may declare that this attribute A extraneous, or the attribute under consideration is extraneous. This is one method that we may apply. Another method is like we may say that attribute A is extra in left hand side of the dependency if F logically implies F dash. If F logically implies F dash. Right? And alternatively, we may say that attribute A is extraneous in right hand side if F dash implies F. So we may go with any of these methods, more simple for the given problem. Right? So if you find that method is simple, you may go with this. If you find that this method is simple, you may go with this. Right? But please remember how we are going to compute this F dash. Right? F dash is being computed simply by omitting the attribute under consideration, either from left hand side or from right hand side of the functional dependency. So by simply omitting that attribute, whatever remains, that is our F dash. Okay, so we may go with either of these methods. So let us proceed. So see here, we are now considering this first functional dependency AB to C, and we want to check whether this A is extra, and we find that this A is extra in this dependency. And what is the reason why we are saying that A is extra in this dependency? See, we are checking like the left hand side of the dependency and we are testing for this attribute A. So, if we are applying this, okay, so what this rule says? This rule says that if F logically implies F dash. So what is my F dash in this case? What is my F dash? If I am considering this AB to C and if I am dealing with this attribute A, if I am checking whether this attribute A is extra, then I am computing my F dash by making use of this rule. So how I am computing this F dash? So simply my F dash in this situation is this set. I am testing for AB to C. I am testing for attribute A, right? So my F dash will become, just I am omitting this attribute A from this dependency. So what remains is to C, A to BC, and once again B to C. But as we have B to C in our set, right, my F dash is F B to C and A to BC. Okay, so what I'll check is, if I want to check whether A is extra, I need to check whether my set F, that means this original set, logically implies this set F dash. Okay, so what is my set F? A, B to C, C, B to C. Whether this logically implies this B to C and A to BC? Obviously. Why? Because B to C is already there in my dash. A to BC, that is already there in my F dash. Right? So, if I am deleting this A from the functional dependency, then AB to C is implied by the other dependency. No need to have this A. Right? So, I may omit this A. A is extraneous and I may omit this A. Correct? I may omit this A, and that is why after omitting this A, what remains is B to C, A to BC and B to C. So B to C comes twice. So we are having only one instance of this. So ultimately my becomes A to BC and B to C after omitting this extraneous attribute A from my dependency AB to C. Okay, now we are having this set of functional dependencies. So what we can do is, if we look at this dependency from A to BC, we are having right hand side of the dependency with more than one. So we need to check now whether any of the attributes in dependency is extra, right? So what we find here is C in this dependency A to B is extraneous. So how we are going to find it out whether the C is extra or not? Once again we are applying this rule. So what this rule says, if I want to check whether the dependency attribute in right hand side is extra, I need to check whether my F dash determines F. Okay, now in this case, this is my F, and what is my F dash now? My F dash is simply, I am considering this C for extraneous, for checking whether it is extra or not. So after omitting this, what remains is my F dash. So I am having now in my F dash A to B, because I am checking for C, and the second dependency as it is. So my F dash is now A to B, B to C. And what I want to check is, I want to check now whether my F dash determines F. Whether my F dash determines F. It out. We are having A to B. We are having B to C. So using these dependencies, it's possible to infer A to B C. Whether this set determines A to B C. Yes? Anybody? Whether these dependencies determine A to B C. Yes, anybody? Whether these two functional dependencies A to B and B to C infer this dependency A to B C. Yes. Actually, the answer is there on screen.
Yes, ma'am.
See, we are having here A to B. We are having here B to C. So if we apply transitivity rule, we may come up with A to C. Right? Now, if I come up with this A to C, then I'll be having A to B and A to C. So after applying union rule, I may have A to B C. Right? So by making use of these two dependencies, it is possible for me to that this attribute C is extraneous in dependency A to B C. Right? So we may omit that. So ultimately from this set now, if I omit this attribute which is extra, what remains? A to B and B to C. So in both the dependencies, both left hand and right hand side of the dependencies are having single attributes. Right? So there is no more chance to check for extraneous attributes. So my canonical cover is A to B, B to C. So this is my set FC. And this was the original set F. So in my original set, I had 4 functional dependencies. And after application of the algorithm for canonical cover, what I can get is only 2 dependencies. And this is why actually we are coming up with set of functional dependencies which is minimal. Right? So instead of checking 4 dependencies for checking violation, now it is possible for me to check for only 2 dependencies for its violation. Right? So the overhead associated if a canonical cover is minimum. And that is the reason why we are computing canonical cover. Right? So, in this example, we have applied these tests. If the problem is more complex, then you may use these particular tests to whether the attribute is extra. Right? You may have similar kinds of questions in your exam. In GATE exam also, you will be having the similar kinds of questions, right? And you need to answer such questions quickly. And that is why whichever method you may feel simple, you may use that method. For simple cases, what I would suggest is, for simple method number 2 is efficient. For some complex cases, this method 1 we may apply. Fine. So let's go to one more example now, wherein we are having a claim. A canonical cover might not be unique. A canonical cover might not be unique. What we mean by this? Given the set of functional dependencies F, we may have more than one canonical covers possible. I'll repeat. Given the set of functional dependencies F, it is possible that we may come up with more than one canonical covers. Right? And to have the better idea about this concept, we are having here one example. So, we are having a relation schema R with 3 attributes A, B and C. We have been provided with the set of functional dependencies with 3 dependencies A to BC, B to AC, and C to AB. Now, we want to find out the canonical cover for this set F. Right? So we want to find out the canonical cover for this set. So let's begin with finding out this canonical cover. So I'm quickly going through this process, but I would suggest you that you know the algorithm. You please try to apply each and every step in our algorithm and come up with the extraneous attributes, right? So, if I apply the externality test to the dependency A to BC, then what I found is both B and C are extra. If I try to apply the externality test to right hand side of this functional dependency A to BC, what I find that both B and C are extra. But I cannot apply this externality test. So I cannot remove both the attributes. So what I can do is, as both the attributes are extra, I may omit this B or I may omit this C. Okay, so C is deleted with this functional dependency F dash, in which I am having, so I am omitting this C. So instead of A to BC, I'll be having A to B. Rest of the dependencies are, if I delete B, then I come up with f dash equal to A to C, B to AC and C to AB. Are you getting me? Yes.
Yes. Yes, ma'am.
Fine. So we are having two possibilities. Either we may omit C or we may omit B because both are extra. Right? So we may have two options now. Okay? Now, if we omit C and if we have this f dash, once again, to whether any attribute is in B to AC or C to AB. So, what we find is, if I take this C, if I check this C to AB, then what I find once again, A and B, both are extra. Right? So, in this situation, I can have is, I may delete this A or I may delete this B. So, once again, I may come up with two sets. FC equal to B to C A after omitting B, or I may come up with A to B, B to C, C to D after omitting this A. If we consider the second case and if we try to find out the extraneous attributes further, we may come up with two canonical covers. A to C, B to A, C to B, and A to C, B to C, and C to AB. So if we follow this process, we will be getting these two canonical covers. If we follow this process, we may once again come up with two different canonical covers. We have not gone through the detailed steps, but I would advise you to go through the detailed steps so that you can arrive at these canonical covers. Right? So I am giving you this as the homework. Please work on your own. Please try to apply the algorithm to find out canonical cover and test whether you will be getting the similar results. Okay? So the essence that I wanted to highlight was the canonical cover might not be unique. So it is possible that we may come up with more than one canonical covers. Right? So I would say you once again to go through this example and work out the process on your own so that you can understand it better. Right? Am I clear?
Yes, ma'am.
Yes,
Fine. So with this concept of canonical cover, now we are going to move ahead with one exercise. So this is for your homework. You take down this exercise. You are supposed to solve this. Given the relation schema R with 5 attributes A, B, C, D, E, the set of functional dependencies F is given as A to B, C, CD to E, B to D, and E to A. And you are asked to compute B plus and the canonical cover. for F. So this is the homework. Right? So let us proceed now with the third normal form known as 3NF. So let us define 3NF and then we'll proceed with the algorithm for 3NF. So we have seen so far the first normal form and the second normal form. The first normal form do not allow us to have repeated groups. So in 1NF, we want all the attribute domains atomic. Right? In 2NF, what we have seen? In 2NF, our relation must be in 1NF, that is the mandatory requirement. And in 2NF, what is the second condition that we mentioned? 2NF depends on, or it is based on, full and partial dependencies. Right? And the second condition in 2NF says that each non-primary key attribute must be fully dependent on primary key. So we do not want any partial dependencies in our relation. So whenever we omit these partial dependencies, we come up with 2. Now, why actually we are discussing all normal forms? Normal forms actually are very much important for reducing the redundancy. I'll repeat, normal forms are meant for reducing the redundancies in the relations. And why we want to reduce redundancies? Because redundancies lead to the anomalies, update anomalies. So, even though the relation to we may have update anomalies into an. So, second normal form may still suffer from the update anomaly. So, we need to have the clear from. So, clear from wherein we can reduce the redundancies from 2NF. Right? So, let us try to define now the third normal form. A relation R on R is said to be in third normal form if and only if it is in 1NF and 2NF. Obviously, the relation must be in 2NF, and whenever the relation is in 2NF, it is obviously in 1. So the first condition in third normal form is the relation must be in 1NF and 2NF. And what next? No non-primary key attribute is transitively dependent on the primary key. I'll repeat, this is the most important condition for 3NF. No non-primary key attribute is transitively dependent on the primary key. Meaning, in 2NF, if transitive dependencies. Then we need to omit those transitive dependencies and we may come up with 3NF. Right? So the second condition in third normal form says that no non-primary key attribute is transitively dependent on the primary key. Right? And if all relations of a database are in 3NF, we say that the entire database schema is in 3NF. Come up with the third normal form. So in the next class, we are going to focus upon the algorithm for third normal form. And we'll see few examples so that you can understand the concept. Right? So, let us conclude today's session. Thank you.